Good evening, everyone, and thank you all for attending tonight's Research Tuesday event, Industrial Greening. My name is Dr. Nigel Rogash, and I'm a Senior Research Fellow here at the University of Adelaide and your MC for this evening. I'd like to start by acknowledging the Kaurna people, the original custodians of the Adelaide Plains, and the land on which the University of Adelaide campuses at North Terrace, Waite and Roseworthy are built. In Australia, we have an abundance of natural minerals and sustainable energy resources, presenting a unique opportunity for us to satisfy the growing global appetite for low-carbon construction and manufacturing materials. Here at the University of Adelaide, we are leading multiple research projects aiming to develop innovative technologies and revolutionise not just heavy industry, but the national economy as well. Australia's iron ore exports currently earn $80 billion annually. Low-carbon products promise to triple this figure, and job creation could reach well into the hundreds of thousands. Tonight, in our first Research Tuesdays for 2021, you will hear all about these projects and technologies and how the University of Adelaide is leading the charge to lighten heavy industry's carbon footprint. Our speaker tonight will deliver a short presentation followed by a Q&A session. Thank you to those who have submitted questions with your registration. We will try and answer some of those at the end of the talk. I also encourage all of our viewers online tonight to submit questions during the presentation via the Q&A section down at the bottom of your screen. We'll do our best to get to as many of those as we possibly can and apologise in advance if we can't get to your questions. Now I'd like to welcome our speaker for tonight, Professor Gus Nathan, who is the Director of the University's Centre for Energy Technology. He's also Deputy Director of the Institute for Mineral and Energy Resources, a specialist in thermal energy engineering, and is a highly published researcher. So please join me in welcoming Professor Nathan.
Thank you, Nick, and good afternoon, everybody. Thank you for coming along. I would also like to acknowledge the Kaurna people on whose land we're standing, and elders past and present, and also like to acknowledge all of the contributors to this talk. I'm part of a very large team, and some of them are here tonight, and others are listening online due to the COVID restrictions, but they're listed here, and their work will be mentioned as we go through. So we've posed this as a question: a low-carbon heavy industry good for Australia? Not because we think there's any doubt that it can be good for Australia, but only because the opportunity does remain to be grasped, and it's only up to us as to how effectively we do grasp it. So the key messages that I'd like to address today are firstly what heavy industry is. I mean, the way we define it is the production of the basic materials that are used in construction and a lot of manufacturing products, which are things like cement, steel and aluminium, including the upstream part of that, which is the mining. And those of you who have been to mining sites and these plants will know they are certainly heavy industries. And the second message is that lowering the emissions from this sector offers a promising future for Australia. We don't need to be frightened by it. Although there are challenges, and I'll mention that, we think the global drivers will outweigh these challenges. And of course, as Nick already mentioned, Australia has the potential to make good use of it because we have the competitive advantage of having the synergy of both outstanding mineral and renewable energy, not only renewable but also some of the blue energy sources which will be part of the transition. Technology development is certainly needed. We can't just switch on the switch today and everything will go green, because it's not yet economically attractive with today's technologies that people would go broke. But it is possible within the 2050 timeline. And so we think that the drivers will outweigh this because the cost of the transition is relatively small, as I'll go into. Technology development is needed for that reason, both for the energy, the heat, and also we also need to manage the CO2 from some of the products that come directly from the minerals themselves. And we'll talk a bit about some of the University of Adelaide's contribution, both in the process, the energy, the CO2 capture and reuse. Also, it won't be the focus of my talk today, but we believe that the markets and social license are also very important, and we do have active contributors in that area as well. So firstly, I think we all realise that the mining and the minerals sector is important to Australia, but we may not realise how important. The total combination of the minerals exports and the manufacturing to these first stage products of metals, etc., is more than double that of our total energy exports, which is LNG and coal combined. It's more than triple all of our combined crops, livestock and associated products. It's more than 4 times the defence sector, although that's not shown on this graph, and much bigger than aged care and fisheries and those kind of other processes. So it's really vital to Australia's economy already. Now, doing nothing is also a risk for us. We need to be acting to benefit, and we'll show. So this red box is that one. What is the potential value? So this is a column. I'm not going to go through all the details, but we're mainly targeting on the conversion of bauxite to alumina, iron ore, and also cement and lime, although not shown here, but simply because this is the exports in millions of tonnes per year, and you see obviously iron ore swamps everything else at some 850 million tonnes per year. And the value, though, of potential value of converting some of these products to a high value carbon products would be converting the iron ore to something like a low carbon metal iron product. Putting those together is the order of 170 billion. Now, it doesn't mean we would be able to get all of this in one go. Obviously, there's been lots of barriers as to why we haven't been able to do it to date, and I'll talk about why we think the low carbon transition offers us a chance to get a much bigger slice of this. So there's been a long dream of probably many in this audience and many listening that we may be able to do more value add, and we believe the low carbon transition offers the chance to capture more of that, and we'll explain why that is. But firstly, a bit more about the challenge. So this is some of the projected trends from the International Energy Agency of the global share of CO2 emissions. The purple box is electricity, the orange is transport, and the light blue is industry combined. And this is projected internationally, the total projected forward 50 years. And what we see is that we expect the electricity sector will decarbonise first, and obviously South Australia is already a long way there. We're currently already at 60% of our electricity grid. So we can see the pathway there is pretty straightforward. Transport is also beginning, but is a bit more challenging, particularly for things like the air transportation and heavy freight. That's why that's a bit slower. But industry is expected to be the slowest. And this is partly because the challenge is greatest, and also because the sector is slow to change because it's got a lot of capital intensive plant, etc. So if we break, this is 32% of current emissions from industry. This is globally. So breaking that 32% down, we see that 3/4 of it is needed for heat and only about 1/4 for electricity. And out of that 3/4, about half is for high temperature heat and half for low temperature heat. So this is partly why the challenge. We don't just need electricity, we need heat, but we also need fuels, as I'll explain shortly. So we know there's lots of emerging pathways out there. We hear a lot about hydrogen, renewable electricity. We can see the wind farms and the PV panels. Solar thermal is also emerging. CO2 capture and reuse, and also biomass and waste. So which of these ones is going to be the answer? Or maybe it's not the answer. More likely, they'll probably all have a complementary role to play, and this is particularly the case in the heavy industrial sector, because, as I'll show, for example, the CO2 capture and reuse, it's not simply about energy. We could get rid of all of our coal and we'd still have some CO2 to manage. So this is a challenge, but the good news is there's lots of investment anticipated globally to meet the challenge. And there are lots of drivers for these. In fact, now many of Australian industry have already committed to carbon neutral by 2050, and these include many of the big players. And it's driven by a combination of reasons. Part of it is investor demand. The investors are now saying we want our companies to be addressing this challenge. But there's also a growing market pool, as I'll show. The global, there's higher value in the green products. Policy and regulation is playing a role, and for example, the Europeans have already got in line to introduce the carbon border tax this year. And of course, there's a lot of new technology emerging. So estimates are, and this, for example, Mission Possible is one of the global think tanks on this area, largely based out of Europe, but they're estimating that just in this sector alone, some $7 trillion is anticipated in the pipeline between 2015 and 2040. Now, a lot of this would occur anyway because plants are getting old and need replacement, but that money is the kind of money that's needed to drive this transition, but it is also expected to become available. And you see these are some of the commitments around the world. You can see Europe, China, US, of course now with the Biden administration, this is also coming into line with the rest of the world. But how about emerging products? These are some of the announcements about Apple and Rio Tinto, BMW, EU, China. A lot of companies now have made commitments to be carbon neutral by 2050. For example, Apple and Rio have also said that they'll have their entire product fleet carbon neutral by 2030. And so these are some of the emerging standards. A number of companies, this one is from Norsk Hydro, have already released low carbon aluminium onto the market, but you can't yet buy, this is not yet carbon neutral, but it's about a quarter of the global average by this low carbon aluminium product, and I'll say a bit about that if you have questions. But currently there is no global standard for these things. They're what companies have developed themselves. So part of the pathway eventually will be, of course, companies will need to have certified by an international standard, which we'll need to comply with in Australia if we want to be part of this. And if we can, then our products can potentially attract a premium. What will that be? Well, we don't know, but we're expecting in the range of 5 to 10%. So the next thing is really that I alluded to it earlier, but the manufacture of these products doesn't only, we couldn't just say we're going to put in PV panels and wind and it's all done. And that's because think processes like iron, this is a reduction process, require a reductant. What is that? Well, this is a chemical to strip away the oxygen from the oxide. So the iron oxide, which is what we get from the ore, is actually iron combined with oxygen into some products such as Fe2O3. There's a number of them. And if we're going to convert that back to metal, to iron, we need to strip away this oxygen, which is a chemical reaction which requires both heat and a chemical. So if we use carbon, this oxygen will go into CO2, but if we replace it with hydrogen, this oxygen will go to H2O. So obviously, the tradition is the conventional pathway is to use carbon as the reductant, but if in the future we switch to using hydrogen and the hydrogen is made renewably or net zero, then we can replace that with remove the CO2 emissions. But we still need the reductant. And also we need heat if we're going to go via the conventional route. So then we have to get the heat and the reductant from a carbon neutral source if we're going to make this iron, which then is later converted to steel, in a carbon neutral pathway. So the current routes are things like a blast furnace, and there's a number of other options. This is a direct reduced iron process, and this one can be run with natural gas commercially, but this is also, even today, the natural gas is actually converted to hydrogen anyway, in a lot of it, not all of it. So there are already, some of these routes are already quite well down the track to be able to produce, replace the conventional route of the blast furnace, which uses coal, with a gas, natural gas, or soon, the plans are already in place to demonstrate it entirely with hydrogen. So for example, this route, the green production with hydrogen is now already largely demonstrated. And so we're not too far from being able to be able to use renewable electricity or another form of low carbon hydrogen. Here it would be shown with an electrolysis unit, which is the commercially most advanced route for renewable hydrogen, needing also water. And then this can be used in a shaft furnace for something like direct reduced, and then an electric arc furnace, which also could be made renewably. So this route is the closest route to the market. You can go down and there are suppliers who will provide it. So I've listed here, Midrex is a commercial supplier who already supply this with natural gas, and have got plans to demonstrate it with hydrogen at industrial scale. So this is very close to the market. And furthermore, we now have got a lot of estimates around what cost is needed for hydrogen to be able to, if hydrogen was able to be produced at this price, this is US dollars per tonne, per kilogram, $1.90 US a kilogram, this is when hydrogen would start to become cost effective with coal, with no other subsidy, in this case in the Chinese market. Currently, hydrogen is around, or historically has been around $10 a kilogram. So you see there's got to be a lot of development, but at different break points, you'll break into different markets. So the good news is that all of the technologies around that are needed in the hydrogen pathway the prices are falling with learning curves, and the learning curves are really every cumulative amount of production. As they upscale, the costs come down. And this is the same with most technologies. You can look in there and you can see solar, batteries, but also these electrolyzer systems are coming down. So we know that there are opportunities we're expecting, even with engineering developments, that costs will continue to fall, which will be part of what is needed to introduce this pathway. But that doesn't mean there aren't also opportunities for new technologies to make a step change. So this is the CSIRO recent study of what they projected the best case cost reduction for hydrogen supply based on the commercial routes with these kind of learning expected, and the the federal government, based on this and other studies, have recently set a target to get to around $2 a kilogram, which is where you would start to be breaking into that cost trajectory of being competitive in things like iron and steel making. However, if we look at the cost of natural gas just as an energy source, of course this is not CO2 neutral, but to break even without it, unless we have some other price benefit, just on an energy basis, we need to get lower costs than this. And so there are also opportunities for us to bring in the next generation technologies, which will then lower the cost down to the next level again. So that's also another part of what is needed to really accelerate the transition longer term. But based on these different technology maps, combined with a knowledge of where renewable energy resources are available, the International Energy Agency have developed an estimate of where in the world we think renewable hydrogen would be cheapest. And you can see that places such as China and Japan, where currently a lot of the manufacturing is done, would have a relatively high cost of hydrogen production compared with places like many parts of Australia. So historically, of course, the cost of shipping coal and the cost of shipping iron ore is really negligible in the total manufacturing supply chain. So this means the economies which are very large, which have got all the downstream manufacturing, the big populations, the economics have favoured them doing all of the manufacture, which is why Australia and also many other countries, Africa, Brazil, we tend to ship the iron ore and coal, and then they get manufactured in those locations. However, we see if we're going to be looking at hydrogen, suddenly hydrogen is going to be potentially cheaper to produce in countries like Australia. But then we have to not only look at the hydrogen cost, production. If the global supply chains are going to change based on these reasons. Not only is hydrogen production cheaper in countries like Australia by potentially about 50%, depending on where you're comparing it with. But also, if you're going to convert if you're going to ship the hydrogen from here to there, you're going to have to also include some storage, and this would add another 40% to the cost. So it's not like coal. The cost of shipping coal is only 1 or 2% compared to its value. But hydrogen is a different story. And on top of that, if we're going to convert the iron ore to iron, this means we avoid shipping. It's lighter because we don't have the oxide, we're only shipping the iron itself, we've removed that, and also we're not shipping water. So these things mean we also can save some 20% on the shipping cost. So put them together, and there's going to be a cost advantage in manufacturing the energy intensive, carbon intensive steps at the locations which have got the coincidence of the renewable or other low carbon energy source plus the ore. So this is really the key game changer, which is going to change global supply chains. However, we have to still do the work to make sure that our ores are suitable for this. We'll come to that in a second. So these are the drivers, but the second point is that even though we've said that decarbonising is going to be relatively expensive, depends what we compare it with. So these are some studies based on even commercially available technology before we start adding, or not the currently commercially known technologies, before we account for potential technology improvements. So decarbonising steel making with known technologies would add about 50% to the cost of steel. So that's a big impost if you're just looking at steel. However, if you look at the additional component to an automotive, a car, where the steel is used, it's only additional 1%. The same with cement. To decarbonise cement based on the pathways that are already known would more than double the cost. We'll say why cement's a challenge. But again, green cement in a green building would only add 3%. Same with plastics. So the point is that percent based on the final product is relatively small, and the drivers, including customer demand and the other policy drivers we mentioned earlier, we believe are certainly big enough to overcome that relatively small increase of 1 to 2%. This is the big driver. So key points thus far. We've defined heavy industry as the production of these basic materials. We've said it's vital to the national economy. That the cost, although it might look big just based on the raw material components, it's small compared to the final bit, so it means it's affordable. Implementing it will change global supply chains because of the need for things like hydrogen, which then is expensive to transport. That can be a 2 to 4 cost advantage. And of course, the potential opportunity for Australia then is enormous, because if we were to convert our iron ore to an iron product, and it doesn't have to be necessarily steel, we think it's more likely to be maybe pellets or HBI or pig iron, but that could easily triple the value. Now, we don't have to get there all in one go, but you can see even a small slice could readily generate an extra 10 billion for Australia. Now, we've shown you these technologies are emerging, so we think, okay, we don't have to do anything because this commercial steel product is now almost there. Unfortunately, it's not quite so simple. Ores ain't ores, oils ain't oils, fuels ain't fuels, and that's because this is just a few photographs of ores in different locations around the world, different sites, and you can see that they all even look very different, and that's because they've got a lot of different other components that come with the ore. You don't just get iron, you get all these other components. So this means every individual processing plant that converts this ore into an iron product is actually tailor-made for that location. You need to understand all the different additional components, how to treat them, and also there's a whole plethora of technology processing options. Which one of these is best for Australian ores? Well, it's not just one Australian ore, there's lots of Australian ores, but each of them is distinctive, and they're quite distinctive from the other ores in other parts of the world. So it means that although it's possible, we have to do work to unlock the opportunity. So net zero technology is still presently pretty much unproven. There are a few demonstrations emerging, but they're still only very selected cases, and costs are still currently too high. So although it's emerging, we can see the path, we know it's coming, we have to develop the solutions in Australia for ourselves. If we wait for others to do it and have to pay them, we'll pay a lot more and we'll also be too late. And many of these supply chains will then be locked up in other locations. So this is why we started the presentation with a question, because we do need to do this work to unlock the value. And the second thing is that we've talked about this heat that we need, and this is a slightly different version of the figure based on energy. And this is the Australian context. In Australia, 42% of our energy is used by industry, and you can see those that use natural gas, coal, these other components. And again, about 40% is for processes above 800 degrees. So we need heat for these processes, and there isn't technology available today to simply switch that to electricity. So these are some photographs of some of what it looks like inside some of these high temperature processes. This is inside a lime kiln, this is an iron pellet process, and this is a glass tank. So if you're going to, we've said we need the heat to drive the chemical reaction, we also need the reduction. And although hypothetically some of these processes could be done with electrolysis, the technologies to do that are at early stage way too small, and we don't have the technology or the time to develop them by 2050. Because the time to prove we have to start with the technologies that are almost commercial now, if we're going to have a chance to roll them out by 2050 across this very large sector. Of course, new technologies will continue to play a role further down the track, continue to drive costs down and improve performance, but we also need to start with the ones that can substitute today. So we need to consider, certainly electrification will play a role within this, but we think alternative fuels will be part of that solution, because you can see it's much easier to put an alternative fuel into these processes. Hydrogen will play a role as the costs of that come down. There are electrical heating technology, but they're not necessarily easily translatable into these processes. They also need a lot more development, things like thermal plasmas. They're currently pretty small scale. They don't run well in the presence of particles, etc. And also CO2 capture and storage. We'll say a bit more about that shortly. So bioenergy. This is one of the studies from the International Energy Agency looking at what we think the projected share of bioenergy into the future is going to be. Now this is, the study is recent even though the data is old, and what you can see is although bioenergy as a whole is increasing, the global share of renewable energy is falling. And this is because it's not increasing anywhere near as fast as things like wind and PV, for example. And also it's constrained. It's much more challenging to harness biomass. You have to be able to transport it, collect it from different farms and aggregate it. So this is limiting the share. So we think it's going to play an important role in the future, but it's probably going to play a different role, and it won't become enough to meet the heavy industrial need by itself. Things like waste is going to become increasingly important, and in fact cement around the world is already a leading user of these alternative fuels, and some photographs of plastics, etc. look like. You can see the mix that are already being used in the cement industry include all kinds of municipal waste, animal residues, solvents, etc., waste oil, and in fact in the cement industry these are much, much bigger than bioenergy. So we think obviously this is going to be another important part of closing the balance in some parts of the industry. But it's important to think that even if we replace all of that energy requirements with renewable energy, or green energy, we still haven't solved the problem entirely. And this is an example of why, because a number of ores are not oxides but they're carbonates. And an example is limestone, which is a commodity not only for cement but also for lime, which is an industrial chemical. This is calcium carbonate. Now we all know calcium is used in our bones. We drink milk or whatever for calcium, and limestone is essentially fossilized atmospheric CO2, and some of it but also may come from dissolved as the rain falls, it dissolves some CO2, which ends up in caves, etc. But limestone is fossilised atmospheric CO2. So when we heat this to convert this to calcium oxide, we liberate CO2. And some 60 to 70% of the CO2 from cement comes from heating this fossilised rock. Although there are emerging substitutes, and we're also working on some of those, including things like calcined clays to reduce this load. The projection is there'll still be needed for certainly by the 2050 time horizon. Cement itself from limestone will be part of the solution, and also limestone is also an industrial chemical itself. So this will continue to be needed, so we need to find ways to manage that CO2. So although there are a number of pathways being developed around the world, including in Europe, we had some of these speaking at our High Temp Forum, we're also working on this ourselves. New technology is needed to manage this CO2 because the currently available CO2 capture pathways are still too expensive, and the current CO2 reuse technology is also immature and still currently expensive, but the costs will come down, but we do need to develop them. We need to adapt also the current processes to meet this 2050 time horizon. We have to also work with the processes we've got as well as developing the new ones, or else the overshoot of CO2 will be too big. And we think by consultation with industry and other stakeholders, we think that in terms of industrial processes, we think that CO2 reuse is more likely to be implemented than CO2 sequestration of this CO2. Sequestration may play a role in the blue hydrogen in places like Moomba, but in an industrial plant, it's typically a long way from any sink. So we think that reuse is a more attractive route, and also sequestration is expensive. If you convert it into a product, you can get a value from it. Of course, this probably won't get entirely to net neutral, so there needs to be other parts of the technology chain developed to get the system to net neutral, net zero, which has to happen, and that can include things like mineral carbonation, biosequestration, etc. So we need all of these components together to get to an economic carbon neutral pathway, but there are technology pathways in train for each of these. One of these pathways is a partnership we're working with a company called Calix, which is an Australian company, although one of their technologies is being developed or trialled in Belgium as part of the CO2 process. This is an indirect reactor which directly captures CO2. It's not yet commercial, but you can see it's at large pilot scale, and we're also working and partnering with them to improve performance and the optimization process to help to take it through to the commercial stage. So in terms of the reuse end, there are also a number of pathways. I'll say a tiny bit about these, but essentially CO2 can be combined with things like water, for example, plus some form of green energy, renewable, etc. And you've got to remember, in our society, we also have a long-term need for carbon products. We need things like tyres, plastics, and from a heavy industrial sector, we also are going to need to have some stored energy. So, for example, if a company is reliant on, say, wind and or renewable electricity, the costs of this can vary from an average of $60 a megawatt hour to even negative for short bursts, or up to $16,000 a megawatt hour for periods when we have very high demand in our grid. So clearly in that time you want to use a cheaper fuel, and things like methanol, which are derived from these kind of routes. You can imagine a company having a big tank of methanol which they can use at a much lower cost. So stored energy, these are the kind of things that could be used. Now, which ones make the most sense needs to be evaluated on a location by location sense, because it depends on their supply chains, where they are, what the markets are. But these are the kind of different routes that are being explored around the world, and there are new technologies developing to bring these costs down. But broadly we see CO2 reuse, probably not so much from the energy source like coal, but from these mineral sources is where we see a long-term need as part of closing the balance. So what we've said, the next step, summary of the next bit of information dump, we think that simply installing PV panels and wind is not enough. industrial processes require heat and reductants, and the current processes are all designed to burn fuels. So we need to adapt current processes as part of the lowest risk route to allow us to meet the 2050 time horizon. Of course, other technologies will also be developed in parallel. And CO2 management is also necessary to look at managing these industrial chemicals from things like lime, and also cement will be part of, some of that will be needed. And we think for these industrial CO2 sources, we think capture and reuse is the most plausible route, combined with other things to completely close the balance. So a few of these other options, I'll just say a couple of words about some of the technologies that we're working on at the University of Adelaide. One of them is a pathway to lower CO2 emissions from alumina production. This is a $3 million program we're working on to look at options, particularly solar thermal, but also looking at hydrogen and electricity. And this is because currently there is no technically or economically feasible path to make alumina at net zero. So we've been doing a lot of work to assess the different techno-economic pathways, comparing these options. We've also developed a novel technology for which patents are in process, and we think that the economic pathway is definitely plausible. Certainly for things like hydrogen at the $2 target would become economic. So we have also a platform of novel technologies under development for low net carbon hydrogen. Some are the green route with renewable energy, and some are from either biomass and waste, and some are from things like natural gas, converting it into these routes, and some combine renewable and the natural gas route together. And I'll just say a snapshot about some of them. One of them is a technology that was originally being developed out of Germany and the USA. Greenway Energy is a US company. This is working on an electrolysis unit, but instead of electrolyzing water only, it electrolyzes water plus sulfur dioxide. And this lowers the electrical requirement by about 3/4. And this generates sulfuric acid, which is then cracked back to, so the sulfuric acid here, this is then goes into a solar thermal reactor, which is then cracked back to the SO2, and this is looped around. And this, so we combine a solar thermal, which has the advantage of being able to use cheap thermal storage, with a system that requires a lot less electricity. And this system is already at pilot scale, and we're working with some novel ways to further lower costs, and also looking at opportunities to integrate this into things like copper production, where there's also synergy with the sulfuric acid pathways. And again, the economics are looking positive, although the technology is at a reasonable scale, but still some time to get commercial. Greg Meether is in the audience, and if you have any questions about this photocatalysis route, he can also address some of the details. But this is another really exciting platform that we've been working on for a long time, with Greg driving it. And I guess the opportunity is with a system such as shown here, which is actually being tested in Adelaide as we speak. And Greg can show people the control panel with the numbers coming out as it runs. But you can see the total infrastructure for this is less than you need for a PV panel plus an electrolyzer. So this is the potential to lower cost. The challenge is that historically these systems have had a low efficiency of solar to hydrogen conversion, and so the work we're doing here is to lower those costs with novel catalysts, also the technology development itself, and also looking at ways to harness concentrated radiation. And this is also potentially being looked at not only for hydrogen but also some of the CO2 reuse platforms, and Greg will be able to take any questions if you're interested. Also working on a novel pathway into blue hydrogen. This is reacting natural gas, and this avoids the CO2 production entirely by pyrolysis, which is also thermal cracking. So basically the carbon, the CH4 is directly converted to carbon, solid carbon plus hydrogen. This is a technology that's been worked on a number of places around the world, and we're also working with University of Queensland here with support of the Future Fuels CRC. The key opportunity here is that the carbon is produced potentially into a valuable co-product. So rather than making a CO2, which is costs you money, you can make a carbon co-product. And molten metals offer a lot of attractive advantages over the solid catalysts that are already under development in other places. And so we've got a very active program on this. And I put Mehdi as a contact if you also want to contact him after this presentation. We also have a large group at the university working on advanced materials. Advanced materials is a lot of work in different types of catalysts, both for battery technology, for some of the types of materials that Greg talked about in hydrogen production, etc. And so Jan is a contact if you'd like to follow through in some of these areas in novel materials. In terms of another component of the solar thermal cost chain is the cost of the heliostats, which focus the radiation. And we have a lot of active work on understanding how to lower wind loading and the cost of heliostats through that activity. And you can contact Maziar, whose email is shown here if you want to find a bit more about some of those details. We also have an active program in electrification of mining pathways and looking at battery integration into that. There's a lot of work being done on electrifying mines and a lot of drivers for this, and we're working on some of the ways to support that penetration with improved technology pathways. And you can contact Ali on this one, his email is shown there. So, in conclusion, the low carbon transition for industry is already underway. Companies have already made commitments to be carbon neutral and are beginning to invest in this platform. And this is driven by the global commitments of industry, of governments, and also by investor demand and what we see as the new markets, which is really driven by the consumer. So the low carbon transition of this sector promises to be good for Australia, and it's driven by the relatively high cost of transport in hydrogen and its need in these reduction processes in particular. One of the estimates, this is by the Grattan Institute, said that there was potential for 65 billion per annum revenue in green steel if we were to go all the way to steel. That would be based on a 7% market share. This indicates the size of this potential value. We think also that other iron products in the global supply chain, such as iron pellets, direct reduced iron or pig iron, are probably going to play a bigger part of the share because this will work with the needs of our global trading partners. There are also new opportunities in alumina and cement and lime, as I've mentioned. However, technology development is needed for us to capture this opportunity. The technologies are on the cusp, but they need to be tailored for each ore and the conditions locally, depending on which resources are available to capitalise on that. And there are lots of technology options, so we need to put them together, but we also need to further develop them to continue to lower costs. And if we do that, of course, we'll also support all of the supporting technologies in Australia, which then makes those manufactured become cheaper because they've got better support. And of course, there are also a range of technologies under development now to meet this need, and you've shown you a snapshot of some of those, both in the process technologies themselves and in the enabling technologies of hydrogen, electrification, solar thermal, and CO2 capture and reuse. Thank you.
Thanks, Gus. That was a really fascinating talk. Okay, so we're now going to move into the Q&A section of tonight. So just a reminder for those of you who are online, you can submit your questions in the small box at the bottom of your screen. Before we get onto the audience questions, we've got a couple of pre-submitted questions that we'll ask first. So the first one is from John, who asks, are green manufacturers prepared to move production into coal mining areas to help mining communities in the transition to renewables?
Yeah, that's a great question, and it actually relates to this study here from the Grattan Institute, which is one that estimated there will be strong potential to grow the steel-making industry because you've got a lot of the people and capacity in regions such as New South Wales. The question of which of these potential pathways are most likely is probably a mix of the above. We think generally that the first pathway for new technology will come from transforming existing processes. It's much cheaper to retrofit a current plant than to build a new one. If you talk to any of the industry in steel, in cement, in alumina, none of them will tell you that they think a new plant is on the horizon in Australia. This is because of the various other competitive processes in the market. Australian manufacturing industry is relatively small by global scale, and so it's a number of challenges which mean that there's not likely to build a new plant in the near term. More likely, the near-term transition will be driven by retrofitting existing plant to change the energy source, to add the CO2 capture and reuse. So we think the transition will begin there. However, we can also obviously imagine that as Australia does begin to transform its iron ore exports into some iron-based product, so more likely in step one might be to clean up the ore to a higher grade. Step two would be maybe pellets or maybe DRI or pig iron. But if we're doing that, it would then be currently, for reference, Australia currently exports 99.5% of our iron ore. That means only 0.5% is currently transformed to iron. So this means if we're going to be even expanding some of that into an iron product, once it gets to that stage, it's relatively cheap to ship some of that around the coast to somewhere like New South Wales, where there's great capacity in. So maybe the steel making may occur in a place like that. We don't know what the pathway is going to look like, but we expect there's multiple drivers. The transition will probably begin with current processes, but then there are massive opportunities to do more, and how that evolves is really a great question. We'll all be interested to see.
Great, thanks Gus. And the second question here is from Austin, who says, Andrew Forrest has famously spoken about leading his company into the green hydrogen economy. How much of manufacturing of steel or any other product would be amenable to converting to green hydrogen? And would it be possible for our entire electricity generation to be from green hydrogen, meaning the whole economy turns green?
This is another great question. And so firstly, I should mention that FMG is a partner with us in our CRC bid for the heavy industry low carbon transition. So we're certainly in touch with the direction, and we're very strongly supportive of the path trajectory that FMG is taking. And certainly the transition to green steel is still going to take some time. It's not going to happen overnight for these reasons I mentioned. But we think that FMG and the Pilbara is a fantastic opportunity for beginning this transition, and we really need to do more analysis to better understand how far and how quickly of these different options the transition will occur. But we certainly expect that the Pilbara will become one of the places where the further value adding is occurring. The question about hydrogen and how much would be needed, I mean, to give you an example, we would need something like 10 times the Australians' current electricity grid if we were going to make enough hydrogen to convert all of that Australians' iron ore into iron and decarbonise our total electricity sector. So it would be a massive transformation, and it's clearly not going to happen overnight, but the pathway is certainly there and the value drivers are there, so that I think obviously if the world is committing to carbon neutral by 2050, then we can expect our share would need to expand all those areas. How far to be doing all of it we don't know, but certainly we expect to take a big slice, and it would take, but definitely we think the carbon neutral 2050 pathway is eminently realisable, and part of that will include, of course, making the grid neutral.
Great. Okay, I'd like to open the questions now up to our audience. So if anyone has a question, please raise your hand. We've got Liz with a roving mic who will come around and get a microphone to you. So does anyone have any questions for Gus? Okay, I've got one just down the front here, Liz.
So how does the current Australian economy, and especially the minimum wage, play into the actual manufacturing in Australia? Because that's a question often raised: is the minimum wage too high, or is it just too expensive to really bring manufacturing into Australia, especially competitively compared to China and other countries?
Absolutely, that's a great question, and obviously one of the points that is historically been made is that the relatively high labour costs in Australia are one of the barriers to our manufacturing sector growing, and historically that has been a contributing factor. Our perspective is we don't think that's going to be a big part of the transition into the future. This is partly because the manufacturing is becoming increasingly automated, so the number of jobs is probably not going to drop per tonne too much, but there's more higher value jobs, and so the amount of production will expand. So what we think is that labour is a relatively smaller component. The other things are bigger drivers, which are things like the size of the Australian economy is very small compared to the global markets, which is why all of our production plants, for example, cement plants, steel plants in Australia are typically, 3 to 10 times smaller than the equivalent international ones, which are lowest cost. And all these things have got economies of scale. So what it means is, for Australia to become economically competitive, we have to understand how we can contribute to the global supply chains. And so the game changer to me is not so much converting iron to steel, because there we're competing with the scale of the other countries. The real game changer comes because of this different cost in the hydrogen and energy, in this energy intensive step of the iron making. We will probably get some of the higher value products as well, but it's mainly the drivers are not so much in labour, they're going to be the cost of the hydrogen transport, which is going to be the big shift, where they'll be much stronger driver than the labour costs.
Okay, another question down here.
Thank you. I think we notice as a general rule that the higher the energy inputs into irrigation, the higher water use efficiency we can achieve within agriculture. You haven't talked much about water, but I wonder whether you believe that, or my question is really with, and as water is such a limiting resource in Australia, particularly for expanding agriculture, whether you believe new, cheaper sources of electricity can basically bring about some revolution within agriculture to radically increase the water use efficiency above what we're achieving at the moment.
Yeah, that's a good question. So in terms of, this talk hasn't so much been about agriculture, but obviously there is a coupling between energy and water use. And obviously if energy costs become cheap enough, then it's possible to get water from the ocean. The question about whether energy would get that cheap is I think speculative at the moment. So obviously there definitely is opportunity for co-production of clean water within the energy mix. I think there's opportunities there. I don't think that that we, at the moment, we can't be sure how much total energy costs, electricity costs will come down. There are different projections. Certainly there are estimates that think it will come down dramatically or significantly. Nevertheless, there's also going to be potentially more costs in managing the variability. So where that goes, at the moment there is a potential for it to come down, but there's also risk of how much it will. So for example, so far the costs in South Australian energy haven't fallen much, even though we've got a higher penetration of renewables. So certainly there's an expectation that it will come down somewhat, but whether it comes down enough to make a massive impact on water availability, we don't really know yet. But it's possible, certainly it will help. And obviously there are others who are probably more skilled in the water question. However, I will make a comment in the water-hydrogen nexus, which does couple with this talk a bit more. And there, I guess, the key point is that the amount of water that's needed for hydrogen utilisation is a very, very small part of the total water budget. So we don't think water is going to be a constraint in terms of hydrogen. It's much smaller than other components. On the other hand, water is always an issue in the general mining and manufacturing area, and there's absolutely our needs to continue to improve there. Things like dry processing and cleaning is going to become an increasingly important part of the technology, which will be part of the upstream part of this puzzle, which will also be needed to address these challenges. So there are certainly ongoing challenges there, and water energy nexus is always part of the struggle, but probably others are a bit better placed to know about the cost of water production than me.
Okay, you have any other questions? Yes, one here.
I did a bit of research before the lecture, and I found out that a lot of countries in Europe, like Denmark and like Switzerland, UK, they're like a lot of green countries in Europe, and I was just wondering, is there any geographic reason behind it? I know it might be a relevant question, but yeah, I just wanted to know why there are a lot of countries in Europe are considered as green countries, and then would you consider Australia as one of the leading countries for sustainable energy and low carbon construction? Yeah.
Thank you. I missed the last part of that question. Sorry, I got the first part.
I was just saying, would you consider Australia as one of the leading countries for sustainable energy and low carbon construction?
Got it. Thank you. Yes. So firstly, the question around Europe certainly is at the forefront in general of green pathways. I think the reasons for that are many and varied. Part of it, I think, is because Europe has a higher population density and has less, because they have less of resources such as renewable energy and also mineral resources. It's driven that recognition has driven their economy to recognise the high value of waste. So, for example, for them, landfill costs are expensive, and hence this is really, and also because they do invest in being technology providers in the global supply chain. That's also part of where their value comes. So we have a lot of partnerships with Europe, and absolutely they are at the forefront of many of these technology, certainly demonstrations, and have many programs in the technology development area. And so it's partly their policy platform, but it's also their context which is supporting that direction. That's also what is, for their cold climate has also driven efficiency in their buildings, for example. So they are relatively, I think, in terms of policy and investment, they are the most progressive and leading. So Australia doesn't have as strong a policy back framework, and certainly historically we've been plagued by a lot of changes in the policy context which has inhibited some of that. So notwithstanding that, because of our extremely good renewable resources, and of course I guess South Australia is probably, at a state level, South Australia is certainly one of the exceptions. At the penetration of renewable energy in South Australia, if it was a nation, would be among the highest in the world. So, but because of our great resource and the high value of that, there's been enough policy support, including through agencies like ARENA, which mean that where I would say whilst the policy end we're not at the forefront, in terms of penetration, we're still, in some regions, we're still doing very well. And so there is still room for improvement, and certainly the federal government's recent announcement of wanting to invest in this high temperature sector is, I think it's recognition of the potential here, and we would say that there's a lot of positives in that direction.
Okay, great. I think we have time for one last question, just up the back there.
Yes, hello. Thank you so much for the insightful presentation. My question is, knowing that renewable energy is required basically to convert into hydrogen? I mean, besides there are other some forms as well. In your view, what is the percentage of renewables we are looking at by 2050? The multiplication, for example, by now we have about 30% of renewables contribution to the grid. What do you think? Will it be, for example, will it be 100%, 200, 300%, or more to actually not only meet the electrical demand by the grid and also to supply to the industries and to export in a form of hydrogen or hydrocarbon and other forms, as you mentioned in the presentation? Thank you.
Yeah, this is a really good question, and obviously no one knows the full answer to that question, but I'll make a number of comments. So generally around the world there is expectation that there will be a growing contribution of electricity to the total energy sector. Currently, for example, in Australia, around about 40% of our energy is from electricity, and the rest is from other sources for industry and for transport. So we do expect that the fraction of energy that is in the sector in electricity will grow. So this means there will be expansion of the network. The question of how much it grows and how much of it comes from either from hydrogen and or from and also in the transport sector. Of course, electrification is already occurring in the transportation sector and will continue. Nevertheless, for example, I noticed KLM, one of the global aircraft transportation companies, have now done a commercial trial of a liquid fuel derived from CO2 and hydrogen and water. So how much of that comes? So within this pathway, what we understand is that the general projections are that longer term, that renewable hydrogen will become cheaper than blue hydrogen. So when that transition kicks over, we don't know. However, we also expect that because of the time scale. So, for example, currently, one of the big green hydrogen production plants in Tonsley, which is one of the biggest in Australia when it was first put in and is still is order of 5 megawatts. So South Australia's grid is 3 gigawatts. So this is currently still small. Now it's upscaling. On the other hand, industry could produce blue hydrogen, which wouldn't yet be carbon neutral, but would still be about 90% neutral. At scale, of industrial scale, they could start building that stuff today. So what we think is to meet the time horizon of industry, we expect to see a mix of some of the blue industry technologies to deliver the scale in the short term, and longer term, the transition will occur to more of the green pathways. But how long that transition is going to occur, which ones kick over and the other ones change, is still unclear. But we do expect that things like natural gas, of course, simple burning natural gas is not going to solve the problem of CO2. On the other hand, if you're going to capture the CO2 at the source and put it underground, and other routes like this together, we have to there's still insufficient understanding of what the lowest cost route to net zero is. And there's going to be a mix of technologies to balance what is not neutral from a pathway like that to get there. So what we say is what we do know is there's going to be a transition required for now. There will be a shift towards electrification, but maybe not 100%, because there's also other ways of making hydrogen that may not go through electricity, such as the photocatalysis route we mentioned. There's a lot of different technologies that are under development at the moment. We don't know how that transition is going to play out. So we do know that there will be a greater penetration of a greater share of electricity in the grid by 2050, and I do believe that a net zero 2050 is possible, but I don't think it's going to be all renewable by that stage. Nevertheless, there'll be a growing trend, probably we think by around that time. The projections are that renewable will be the cheapest.
Okay, fantastic. So unfortunately we're out of time, but I'd like you to all join me once again in thanking Professor Gus Nathan for a fantastic talk.
Thank you.
And also a big thank you to you, our audience, for coming here tonight and also for your participation. It's been great. So this has been our first Research Tuesday for 2021, and on behalf of the Research Tuesday team and the university, I want to thank you all for coming out here tonight. We're extremely excited to be back delivering these presentations here on campus and also to our online audience. So we look forward to inviting you back in March to learn more about the university's research into the impact of COVID-19 on housing. Be sure to sign up for our mailing list to receive the latest information about that and all of our Research Tuesday related news. Thank you once again for coming and for tuning in tonight, and we hope to see you all next time. Good night.